So this is just repeating what's on the previous page. It says, in other words, the velocity function is the derivative of the position function. Velocity can be negative, 0, or positive. Remember, velocity has direction. Speed is the absolute value of the velocity. So if they said, how fast were you going? They don't care which direction. They don't care whether it's positive or negative. They just care about the amount. So it's not negative 32 feet per second. It's 32 feet per second. That's what they're looking at on that one whenever they say speed. Okay, it says the position of a free-falling object neglecting air resistance under the influence of gravity can be represented by the equation S of t equals 1/2 g t squared plus v naught t plus s0. That's your position function. It says with s0 is the initial height of the object, v0 is the initial velocity of the object, and g is the acceleration due to gravity. On Earth, the value of g is approximately 32 feet per second, or 9.8 meters per second. Okay? Whew! What the heck did they just say? What they essentially just said is if you have a position function for any object on Earth falling without wind resistance, it's important that you know there's no wind resistance here, and all we're doing is measuring the height of the object dropping off a building, for instance, it would always be negative 16 t squared plus v naught t, which would be your initial velocity. So for instance, here we just dropped that billiard ball on the last problem, so it started from rest. If we threw that ball up in the air first, then you would have a positive initial velocity, meaning it was going up. If we threw that ball downwards, we would have had a negative initial velocity, meaning it was going down. But we just dropped it. We let it go from rest. We didn't throw it, so our v naught was 0. So you didn't even look at that original velocity. And then it's plus s naught, where again, this is your initial position. So this is starting height. And this is your starting velocity. Okay, and you can do the exact same thing, and this is always in feet per second. Okay, this one's rated in feet per second. So your position would be in feet, your time would be in seconds, your velocity would be in terms of feet per second. Okay, what they're saying is the exact same thing could happen if you used it for meters, 9.8 meters. We would just have to divide that by 2. And we would get 4.9. So if this were in metric, S of t would be equal to, negative 4.9 t squared plus v naught t plus s naught. The exact same formula, except now your position's in meters, your velocity's in meters per second. Okay, so that's the difference in that one, feet versus meters. Okay, let's look at this one right here. Great problem, could be on the test, so I want you to pay attention to this. It says at time t equals 0 seconds, a diver jumps from a platform on the diving board that is 32 feet above the water. See this example in 3.22 figure. It says the initial velocity of the diver is 16 feet per second. It says velocity is the positive when the object is rising and negative when the object is falling. So a positive number means you're going up, a negative number means you're going down. Notice this diver jumped upwards, so my initial velocity is going to be positive. And if you notice, that's what they say, 16 feet per second because it jumped up. If that diver jumped straight down, that would be a negative 16 feet per second. But it's positive because the diver jumped up. Okay? All right, so let's look at this. When does the diver hit the water? Well, the first thing we need to know is the position function. So what is that position function? What is that position function going to be? Well, it's always S of t for position. Why? I have no idea why they use the letter S, but they do. And remember, it's always negative 16 t squared plus v naught t plus s naught. Okay, why did I know it was negative 16? Because I see that it's measured in feet and it's measured in feet per second. If it was the measured in meters, I'd have to use that negative 4.9, but it's not. It's measured in feet. So let's go back and let's reread this. It says you're started at 32 feet above, so that's your initial position. And then it also says your initial velocity was 16 feet. So that gives us that amount right there. So let's rewrite this position function. Here's S of t. Sorry, let me use black on that one. S of t would equal negative 16t squared plus our initial velocity being 16, so that would be plus 16t. And then plus that initial position, which would be 32. And then it wants to know when the diver has hit the water. And if you think about that, what does it mean when you hit the water? When you hit the water, that means your position, your height above the water would be 0. So what do we want to do? We want to set that equal to 0 and solve. Okay? This is a quadratic equation. Negative 16t squared plus 16t plus 32 equals 0 is a quadratic equation. I don't care how you solve this problem, whether you use the quadratic formula, whether you try to use factoring, whatever you want to try to do, you need to be able to solve quadratic equations. That is a problem from beginning and intermediate algebra, so you need to know how to do this. For instance, I see everything as divisible by 16, or in this case, I'm going to divide everything by negative 16. These are all nice numbers. They clearly picked some nice numbers and rigged it for us, so it wouldn't be too bad. So when I divide everything by negative 16, I'd end up with t squared. Well, it wouldn't be plus t. 16 divided by negative 16 would be minus t. 32 divided by negative 16 would be minus 2 equals 0. Now I need two numbers that multiply to be negative 2. Again, I'm trying to factor. So I'm going to multiply numbers that need to be negative 2 and add to be negative 1. That would be t minus 2 and a t plus 1 equal to 0. I've done no calculus whatsoever. Now I'm setting each one of those factors equal to 0. I'm going to get t equals 2 for the first one. T plus 1 equals 0 is going to give me t equals negative 1. T is the amount of time, so negative 1 second doesn't make any sense here. We need a positive number of seconds. So when does the diver hit the ground? The diver is going to hit the ground exactly at 2 seconds. Pretty cool. We can actually figure that out. Okay. Now it says what is the diver's velocity on impact? So we need to find v of t, which is equal to s prime of t, right? So what's the derivative if we know s of t? I'm just going to remind myself is negative 16t squared plus 16t plus 32. So that's going to tell me that velocity, which is the derivative of that, would be negative 16 times the derivative of t squared, which is 2t, plus 16 times the derivative of t, which is just 1, plus the derivative of 32, which is just 0. So I'm getting my velocity functions equal to what? Negative 32t plus 16? But I need to look at that at t equals 2 because it's when it hits the ground. So that tells me v of 2 would be equal to negative 32 times 2 plus 16. Plug that into your calculator. I'm getting negative 48. And then remember, this is velocity. Velocity is measured in this case, feet per second. So when the diver hit the water, they were traveling at a rate of negative 48 feet per second. So we had some really cool application here. We know we can, just from reading the problem, set up the initial position problem. Gravity is always constant on every object, so it's always going to be of this form. Plugged it in, set it equal to 0 to see when it hit the ground, found the time that it hits the ground, found the velocity by finding the derivative, plugged in that time 2 seconds into the derivative, and we were able to find the velocity. So I can, without even watching the diver, tell you exactly when they're going to hit the ground and exactly what speed or velocity they were traveling when they hit the ground. Really, really cool application there.